Hello and welcome to today's video. In this video, we are once again going to talk about integration. Specifically, we have defined integration formally. What we have not done so far is we have not actually computed integrals. And before we start doing so, it's helpful to collect a few properties of the integral. And that is going to be the topic of this video. So we are talking about properties of the integral. We collect most of these properties in the following theorem. And you notice that some of these properties have already been discussed in the connection of step functions. So as usual, we'll say that I is an interval of the form AB, closed interval. But as you know, the boundaries don't really matter for the integral, so it doesn't really make a difference whether that's closed or not. Now, the first property is referred to as the linearity of the integral. That means if we have two functions, so let f and g be functions defined on I with values in R, let those be integrable over I, and also let lambda and mu be two constants, two real numbers. Then we can have a look at the function lambda f plus mu g. And this function is also integrable over I if f and g are integrable. And we can express the integral over this interval or any subset of that interval. So the integral of lambda f of x plus mu g of x dx is the same as lambda times the integral of f of x dx from a to b plus mu times the integral of g of x dx from a to b. In other words, the set of all integrable functions is a vector space. That is the first part here of the property, saying this linear combination of two integrable functions is once again integrable. And second, the integral is a linear mapping that assigns to every element of a vector space, so every integrable function, a real number. And that mapping is linear, and that is this second property here. So, in other words, the set of all integrable functions is a vector space and the integral is a linear mapping on that space. Now that property here, the first property, is also referred to, unsurprisingly, as the linearity of the integral. Now the second property is also something that we have already seen for step functions. That is the monotonicity of the integral. Again, let's say we have two integrable functions, so let f and g both be functions on I with real values, let both be integrable. Then, if f of x is less or equal to g of x for all x in I, then this also holds for the integrals. So then the integral of f of x dx from a to b is less or equal to the integral over g of x dx over the same interval. And as I said, this property is known as the monotonicity property of the integral. In particular, of course, every function f of x dx is less or equal to its absolute value. So the integral over a function is always less or equal to the integral over the absolute value of that function. So that's the second property. And the last one refers to manipulations of the boundaries of the integral. It's known as the additivity property. So for that we need a point in the interval, so let gamma be a point in the interval AB. Then a function f defined on I is integrable over I, and remember I was AB, if and only if it is integrable over the two parts defined by gamma, over the interval a gamma and the interval gamma b. So we take this gamma right in the middle and we divide that interval into two halves using that gamma. And also we have the following relation: the integral of f of x dx over this whole interval is equal to the integral from a to gamma of f of x dx plus the integral from gamma to b of f of x dx. So you can split that up at any midpoint in the interval. And as I said, this property is known as the additivity property of the integral. Okay, then there's also bounds on the integral. That can also easily be explained through the definition. So let's say we have an integrable function, let f I to r be integrable. And let two numbers, small b and capital B, real numbers, be given such that, well, small b is less or equal to f of x, and that is less or equal to capital B for all x in the interval I. Then the following inequality holds: b times the length of I, and that length of I is simply given by b minus a, is less or equal to the integral of f of x dx from a to b, and that is less or equal to capital B times the length of the interval b minus a. So graphically, what happens here Now let's say we have a function that, for example, looks like this here. And we are interested in the behavior of that function on this interval here. We start here, so that be our point A. And the last point in the interval, let's say this point here, so that is B. So that's the interval we're interested in. This here is then the length of the interval. And then, of course, we have a lower bound on this integral. Remember, the integral represents basically the area below the curve here. So this here is the integral. All right, so that is the integral of f of x dx from a to b. Then we have a lower bound. We get that by just taking the lowest point or anything below that lowest point of the function on the interval, which is here in that case. So the area of that rectangle here, this is this left part of the inequality. That's the middle part. And the top part of the inequality is then this here. So we need a capital B, a value that is at least as large as the highest function value on the interval. So for example, we could take this one here. And then again, we consider the rectangle formed by that. We get that rectangle, and as you can see, the area of that rectangle is larger or equal to that of the blue area. So this motivates this inequality here. Now, sometimes it's useful to integrate over certain variations of f, let's say. We have already seen the absolute value. There's two other variations that are sometimes of interest, and that's the positive and the negative part of f. So let's quickly summarize what we know about the integral of those. So let f again be an integrable function. Over I. And let's define f plus and f minus as the following. F plus of x is defined as the maximum of either f of x or 0. So that means if f of x is positive, then we just take the function value. If f of x is negative, then we take 0. So we cut the function off at the x-axis at 0. And for f minus, we do the reverse. Plus, we flip the function up. So what we do now is we take all the parts below the x-axis and then we flip them up. Or in other words, precise definition, we take the minimum of f of x or 0. So any negative function values will be taken as they are. Any positive values will be cut off at 0. And then we flip by adding a minus sign. So negative function values become positive and 0 just stays 0. So this is f minus, the negative part of the function. Then, of course, f could be written as f plus minus f minus. The absolute value of f could be written as f plus plus f minus. Remember, f minus is also non-negative now. And these functions are also integrable. So the functions f plus, f minus, and also the absolute value are integrable over I with, well, we get is the integral from a to b of f of x dx can be written as, unsurprisingly, the integral of f plus minus the integral of f minus. And compared with the absolute value, the following relation holds: the integral of f of x dx, and then taking the absolute value of that, is less or equal to the integral over the absolute value of f of x dx. Just as a quick illustration of how these functions here look like. So let's say we are in a situation like this here. We have a function that looks like this. Then the positive part of that function can easily be sketched. It's just the positive part here. So this part of the function where the function is at least 0, or where it becomes negative, f plus will just be 0. So f plus is 0 here and here. So that is f plus. Right, the blue part is f itself. And then f minus is a little more complicated. So f minus is 0 where f is positive. So along this part here, f minus will simply be 0. For the parts where it's negative, please remember that f minus is going to be flipped. So here, we don't just take this as f minus, but we flip it up. So this here is f minus, right? So it looks kind of like this here, and here we similarly get an f minus looks roughly like this, right? So this is f minus here. Okay, so this is how these functions look like. Finally, one more theorem about integration that will be useful, especially in some theory, some powerful theory we will develop in just a few videos. That is the so-called intermediate or mean value theorem of integration. What that says basically is that the value of an integral can also be represented as a very simple rectangular area given by a value of the function itself that we integrate at a certain point. I'll write it down precisely. It's probably easier to understand the formula. So as usual, let I be an interval of the form a to b, subset of R, and let f be a function on I that is continuous. And that's the one additional assumption that we want. It's going to be continuous. And as you know, a continuous function on a closed interval is also integrable, so we don't have to worry about that. And the statement is, then there exists a point x tilde in that interval, a to b, such that the integral from a to b over f of x dx is equal to the function value at that point x tilde times the length of the interval b minus a. So basically this here is a rectangular area of a rectangle, and this on the left is the integral. So in other words, the integral, the value of the integral, can be expressed by some rectangular area, positive or negative, so this might have a sign, for a certain function value in that interval. It's not clear what that function value is, but we have a guarantee that such a function value exists. And we'll need this in just a few moments to prove probably the most important theorem in the theory of differentiation and integration ever, the fundamental theorem of calculus. So this will be one of the upcoming topics, and as usual, I hope I see you then.